In this videocast, we'll take a look at Chapter 16, an overview of acids and bases. First, some definitions. Savante Arrhenius said in the late 1800s that acids were substances that, when dissolved in water, increased the concentration of hydrogen ions. And then he said that bases were substances that, when dissolved in water, increased the concentration of hydroxide ions. This limited the number of things that were acids and bases, and so Bronsted and Lowry came along in the early 1900s and said that acids were proton donors and bases were proton acceptors. Remember that protons are H plus ions, hydrogen ions. A Bronsted-Lowry acid must have a removable or acidic proton. A Bronsted-Lowry base must have a pair of non-bonding electrons for that hydrogen ion to go and glom onto. If it can be either an acid or a base, it is called amphiprotic, and 3 amphiprotic examples are given right here. Notice that water is one of those things. It can be an acid or a base. It can donate a hydrogen or it can accept one. So what happens when an acid dissolves in water? Well, water acts as a Bronsted-Lowry base. You can see here HCl, which we memorized as a strong acid, gives away a hydrogen to the water. The water readily accepts it. When this happens, a conjugate base of the acid and a hydronium ion are formed. This HCl molecule has now become just Cl-. This was called an acid, HCl. The Cl- is now called the conjugate base. Water up here was the base. It accepted a hydrogen right here, and now it is actually called the conjugate acid. It's also called a hydronium ion because it is H3O with a positive 1 charge. The word conjugate comes from the Latin word conjugare, meaning to join together. And you can see right here, HNO2 is an acid. It gives away a hydrogen, and it becomes NO2-, which is called the conjugate base. It's what's left over after the acid has released its proton. H2O is the base, accepting the proton, becomes the conjugate acid, and once again looks like the hydronium ion, H3O+. Reactions between acids and bases always yield a conjugate base and a conjugate acid. So how do you know the strength of an acid or a base? Well, remember, strength in acids or strength in bases means how much the acid or the base dissociates in water. In other words, breaks up into its ions. Remember, it doesn't have anything to do with its molarity or its concentration. It only has to do with how well it dissociates. And we memorized the strong acids and the strong bases way back in Chapter 4. You can see up here are strong acids HCl, H2SO4, and HNO3. Their conjugate bases, after they've released a proton, would be Cl-, HSO4-, and NO3. And notice they have a negligible, or like 0, basicity. Whereas things that are strong bases down here, when they glom on or grab a proton, they become negligible strength acids. Their conjugate acids are just weak non-acids. You can see in here we have weak acids and weak bases, and they become conjugates of one another, and they are weak acids and weak bases. Weak acids only partially dissociate in water, and conjugate bases are weak bases. Substances with negligible acidity do not dissociate in water. So these things down here, they don't dissociate in water because they have negligible acidity. They don't break up to give you 2 H- or something like this in terms of H2 because they're so weak. Well, in any acid or base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. And you can see here, HCl, a strong acid, will readily give up its hydrogen to H2O to form H3O+, and the conjugate base, Cl-. H2O is a much stronger base than Cl-, so the equilibrium lies far to the right. K is way, way bigger than 1. It's on the order of 1,000 or so because there's tons of product and very, very, very little reactant. If we look at this reaction in the backwards direction, from this side, the product side, to the reactant side, we can see that C2H3O2- is a stronger base than H3O+, and therefore it creates this acetic acid and this H2O. And the equilibrium would lie far to the left because this is a weak acid, and water, of course, can be a weak acid or a weak base. And this would be the stronger base, and therefore it would pull the hydrogen ion away from the H3O+. And the equilibrium would lie far to the left, and K would be a decimal point, like 1.1 times 10 to the negative fifth, or something like that. As we have seen, water is amphoteric. In other words, it can act as an acid or a base. In pure water, a few molecules act as bases and a few act as acids. And every once in a while, two water molecules bump into each other and act that way and form this conjugate acid and this conjugate base. Water autoionizes. Now, it doesn't do this very much, a very, very small extent. You could find the equilibrium constant of this by taking the products and dividing it by the reactants, except notice the reactants in this case are pure liquids, and so they are not even involved in equilibrium constant. As I said before, this is referred to as autoionization. The equilibrium expression for this process is products divided by reactants. Remember, the reactants are pure liquids, so they're not involved in it. This special equilibrium constant is referred to as the ion product constant for water, and it's renamed no longer Kc or Kp, it's called Kw or Kdub. It turns out that at 25 degrees Celsius, Kdub is always 1 times 10 to the negative 14th. Notice it's a tiny number, 10 to the negative 14th. That's because there's not much of this H3O or OH minus that's produced in pure water. That's why water is very neutral. So how do we know whether something's acidic or basic? Well, we use a rating scale. It's a scale called the pH scale, and it's defined as the negative base 10 logarithm of the hydronium ion concentration. The pH is equal to the negative logarithm of H3O plus, or the hydronium ion concentration of any solution. In pure water, since Kw is equal to H3O plus times OH minus and is equal to 1 times 10 to the negative 14th, H3O plus must be equal to OH minus, and therefore H3O plus is equal to 1 times 10 to the negative 7th. If you take the negative logarithm of 1 times 10 to the negative 7th, guess what? You get a pH equal to 7, because remember, pH is equal to the negative logarithm of 1 times 10 to the negative 7th. Remember, a logarithm is nothing more than the exponent right here, and the exponent right here is negative 7. And of course, we're taking the negative of that, which gives us 7. That's why water has a pH of 7. An acid has a higher H3O concentration than pure water, so its pH is less than 7. And a base has a lower H3O concentration, H3O plus concentration than pure water, so its pH is lower than 7. These are the pH values for several common substances. You can see that milk is just slightly acidic. Rain, slightly acidic. Bananas, tomatoes, wine, Coca-Cola, and vinegar are all acidic. And up here, it's interesting to see that human blood is just slightly basic. Slightly basic. Baking soda, borax, milk of magnesia, and lime water are also very basic substances, or increasingly basic substances until you get down here to bleach. So are there other p scales, other things that tell us to take the negative log of a quantity? Certainly there are. There's also some similar examples like the pOH, where we take the negative logarithm of the OH minus ion concentration. There could be the pKw, in which we'd take the negative log of Kw. We also will find out that there's some other p scales later in this chapter that we just take the negative logarithm of whatever number that is. The p in front of here just means take the negative log of it. So watch this. Here is the autoionization of water's equilibrium constant, and we know that the negative log of H3O plus the negative log of OH minus will be equal to the negative log of Kw. The negative log of 1 times 10 to the negative 14th is 14, and we know that this thing, negative log of H3O plus, is called the pH, and the negative log of OH minus is called the pOH, so we can say pH plus pOH is equal to 14. A real handy equation that in the next video cast you'll see us use a lot. So how do we measure pH? For less accurate measurements, we use litmus paper, or we use different indicators, methyl violet, thionyl blue, methyl red, phenolphthalein, etc. For more accurate measurements, we can use a pH meter, and we'll use these in a number of labs. So, let's talk about strong acids. You'll recall that the 7 strong acids were hyperhickel high, honohickel low, H2SO4. And remember, when we say hickel low, we mean HClO3 and HClO4. These 7 strong acids, remember, have an equilibrium constant of greater than 1 because their equilibrium would lie far to the right. And by definition, they're strong electrolytes and exist totally as ions in the aqueous solution. For monoprotic strong acids, the H3O plus ion concentration is equal to the concentration of the acid, because when they dissociate, this H3O plus is the concentration that was this acid over here. Oh, by the way, let's go back here just one second. If you take a look at this, this is a strange word, monoprotic. The prefix mono means one, and protic here means proton. So a monoprotic acid would mean that it has one hydrogen ion attached to whatever the anion would be. You can see that all the strong acids are monoprotic, having one hydrogen, except H2SO4. This is called a diprotic acid because it has 2 acidic hydrogens, or 2 hydrogens in it. We'll talk more about diprotic and what are called polyprotic acids later on in this video cast. Strong bases are the soluble hydroxides, which are the alkali metals, and the heavier alkaline earth metals. Remember, they form a B on the periodic table. Again, these substances dissociate completely in aqueous solution, giving us positive cation and a lot of OH minus. For a generalized acid that's weak, we can write the generalized equilibrium expression by saying the acid will react with water, and we'll get A minus and H3O plus. The acid releases its proton and gives it to the water. And we can write the equilibrium constant expression as H3O plus times A minus divided by HA. This equilibrium constant is now renamed, and it's called the acid dissociation constant. And so instead of calling it K sub C now, we call it K sub A. K sub A for acid. Guess what? We do the same thing for bases. We'll see in a few slides. The greater the value of Ka, the stronger the acid. Because if you look back at this slide, what's on the top of the equilibrium constant? Well, the products right here. If you have a lot of products, you'll have a high number for equilibrium constant, and therefore we consider it to have lots of ions when it dissolves. So you can see hydrofluoric acid, not a super strong acid, 6 times 10 to the negative 4th, whereas phenol is a very, very, very weak acid, 1.3 times 10 to the negative 10th. We'll do a number of calculations with weak acids and bases in the next several video casts, and sample problems in those will include using Ka to find pH, or using pH to find Ka, vice versa. And we'll also look at problems where we'd find something called percent ionization. In other words, how much of the hydrogen ion dissociates, or how much of the OH minus ion dissociates to form the acid or the base. Stay tuned for those. So how do you calculate percent ionization? We'll take a look at one of these problems in a little while, and a lot deeper at the other kinds in our next video cast. But percent ionization is defined as the H3O plus ion concentration divided by the initial concentration of the acid times 100. So in this example, we have a hydrogen ion concentration of 4.2 times 10 to the negative 3rd, and we had an initial concentration of HCOOH as 0.1 molar. So to find the percent ionization, then we would just take the H plus, divide it by the initial concentration, and multiply by 100. Turns out that this is 4.2% ionized. It'll turn out that 5% is kind of a magic number for us for percent ionization. So going back, we talked about monoprotic acid, but what about acids that have more than one acidic proton? These are some examples right down here: carbonic, citric, oxalic, phosphoric, sulfurous, sulfuric, tartaric. Okay, you can see they have more than one H in their formula. If the difference between the Ka for the first dissociation and the subsequent Ka values is 10 to the third or more, the pH generally only depends on the first dissociation, which will become very, very important when we do calculations using Kas to find the pH of a particular acid. You can see here, here's the Ka1 and the Ka2. That would be for the second dissociation, that's why it's a 2. And then some even have a Ka3 because they have 3 acidic protons. So you can see here H3PO4 has a Ka3. When it releases its third proton, it would have that Ka value. So let's look a little closer at weak bases. Bases react with water to produce hydroxide ions. And of course, they've got to have something that can act acidic next to them as well. NH3 is a weak base. It pulls a hydrogen away from water. It's a proton sucker. It pulls a hydrogen away from it and makes it be the conjugate acid, and therefore leaves water straggling without a hydrogen to be the conjugate base. The equilibrium constant expression for the reaction then is HB, the base that's formed on the right-hand side, and OH minus that's formed on the right-hand side, divided by B, where K sub B is now called the base dissociation constant because it's for a base. Here are a bunch of examples of weak bases. Notice the carbonate ion is a pretty good weak base, 1.8 times 10 to the negative fourth for a Kb. The hypochlorite ion is a pretty good weak base. Notice these are their conjugate acids that they maybe came from. You can see that a lot of weak bases are things that came from acids. Ammonia is a good example of weak base, the classic weak base example. So how can you find the pH of a basic solution? We'll do a number of these problems as well, so I'm going to skip through these slides kind of quickly in the next few video casts. You can see here, you can write the Kb expression, and if you look up the Kb of NH3 in the back of your book, by the way, Appendix C has tons of Ka and Kb's listed for lots of weak acids and bases. You can plug in this 0.15 molar down here, make an ice table, and you'll make a neat assumption about this X that's lost right here. And it allows you to calculate for the hydroxide ion concentration, which is 1.6 times 10 to the negative third. You'll end up, therefore, finding out that you can take the negative log of that to find the pOH, subtract that from 14 to find the pH. That might have been way too fast for you, but hang on. Next couple video casts will go in depth and in lots of detail with those equations. So let's take a deeper look at Ka and Kb. Well, they're related. Ka times Kb will give you Kw. Therefore, if you know one of them, you can know the other. So if you know the Ka of an acid, for instance, HF right here, you can find out the Kb of the conjugate base. You can find the Kb of the conjugate base right here, simply by taking Ka and having it be the denominator below Kw to solve for the Kb. So if you know one, you can know the other, and in the next video cast we'll do some math equations with those. So what about salts? Are salts acidic, basic, or neutral? Well, the word is, it depends. And if you have an anion of a salt, it can act as a base, depending on where it came from. If the anion came from a weak acid, it will act as a base. As such, they can react with water in what's called a hydrolysis reaction to form OH minus and the conjugate acid. And you can see right here is the anion reacting with water to form the weak acid and conjugate acid and the conjugate base, OH minus. What about cations from a salt? Well, cations with acidic protons, like NH4+, will lower the pH of the solution. Most metal cations that are hydrated in solution also lower the pH of the solution. They act acidic. We'll find out why these metal cations act acidic in a little while. Attractions between the non-bonding electrons on oxygen and the metal cause a shift of the electron density in water. This makes the OH bond more polar and the water more acidic. And greater charge and smaller size make the cation more acidic. Greater charge and smaller size. Greater charge and smaller size. So let's summarize the effect of cations and anions. First, an anion that is a conjugate base of a strong acid will not affect the pH at all. So if it's chloride ion, bromide ion, iodide ion, which came from HCl, HBr, or HI, They'll do nothing in solution. They will not affect the pH. If it's an anion that is a conjugate base of a weak acid, it'll increase the pH. So if the salt had an anion in it that came from a weak base, from a weak acid, it'll increase the pH because it'll be acting as a weak base. A cation that is the conjugate acid of a weak base will decrease the pH because it will act acidic. We'll have a lot of examples of these in the next video cast. Cations of strong Arrhenius bases will not affect the pH, and other metal ions will decrease the pH because they act acidic. When a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, the effect on pH depends on the Ka and the Kb values. Whoever is bigger wins and causes it to be either acidic or basic. So what factors affect an acid strength? The more polar the bond between hydrogen and its anion, and or the weaker the hydrogen and its anion bond, the more acidic the compound. So we can see here left to right on the periodic table, it increases acid strength when you have a stronger bond between the hydrogen and the more electronegative chloride. Conversely, as you look up and down in the group 17 or group 7 ions, hydrofluoric is actually a weak acid because the bond is so strong between hydrogen and fluorine. But HCl becomes a strong acid and is easily dissociated because the bond between chlorine and hydrogen is not nearly as strong as HF. And you know, as you go down to bromide, HBr, and HI, the bond actually becomes weaker because the electronegativity of bromine and fluorine is less, and therefore those are super strong acids as well. Acidity increases from left to right across a row and from top to bottom down a group. In oxyacids, acids that contain oxygens, in which an OH is bonded to another atom, Y is the more electronegative, Y, the more electronegative Y is, the more acidic the acid. So, taking a look at chlorine versus iodine when they have an OH attached to them, the more electronegative chlorine causes to be a little bit stronger acid. Notice it's 10 to the negative 8th here versus 10 to the negative 11th. So you can see here as an example, chloride, bromine, and iodide. Going down the periodic table, chlorine is higher than bromine, which is higher than iodine, which means that chlorine is more electronegative, therefore it has a higher Ka value. Secondly, for a series of oxyacids, acidity increases with the number of oxygens. So the more oxygens that you wrap around the central atom, the more acidic the oxyacid becomes. And you can see HOCl versus HOClO versus HClO3 and HClO4. They become increasingly higher values of Ka as you add more oxygens around the chlorine. Lastly, resonance in the conjugate base of carboxylic acids stabilizes the base and makes the conjugate acid more acidic. So you can see here, if you put an H plus on the end right here of this O, it would be what's called a carboxylic acid. C2H3O2 with an H tucked on it would be called acetic acid. And if it releases the hydrogen, now this area of the molecule can have resonance between the oxygens. By sharing this double bond, this whole thing becomes a much more stable conjugate base, therefore making the substance be more acidic. Lastly, there's one other definition of acids and bases. We began this by talking about the Arrhenius type of acid and base, and then we spent most of the time talking about the Bronsted-Lowry definition of acids and bases. Lastly, we'll talk about Lewis acids. The Lewis definitions are defined as electron pair acceptors for acids, and bases are defined as electron pair donors. Atoms with empty valence orbitals can always be Lewis acids. Notice here we have NH3, which we classified before as a base, can donate electrons to BF3, which has an empty valence orbital. And since it can accept electrons, it's considered BF3 right here, a Lewis acid. Notice it couldn't be a Bronsted-Lowry acid because it doesn't have a hydrogen ion in it to give away. It doesn't have a hydrogen to give away. But in this broader definition of acids called Lewis acids, it can be an electron acceptor, and therefore BF3 can be defined as an acid. NH3, of course, can still be defined as a base. Lewis bases are defined as electron pair donors, and anything that can be a Bronsted-Lowry base is also a Lewis base. Lewis bases can interact with other things than protons, however, and can give their electrons away to things like, for example, cations, metal ions that have charges and are missing electrons. That's why metal ions can act or make solutions be acidic. We'll add more to these as we finish our video cast series with many, many examples.